Hello everyone, and welcome to the Scalable Software Architectures class, Lecture 1. In this class, we're going to talk about different types of scaling and basically introduce you to what this class is all about. I created this class a year ago now, a little more than a year ago, because I thought, based on my experience in industry as a software engineer and software engineering manager, that the typical computer science curriculum, the classes that computer science students take, we're missing something. There's a gap there. In CS classes, especially in the first few classes, students learn about writing programs. Of course, you have to start somewhere, and you start with the basics. Students learn about writing programs that run on a single machine and are single-threaded. They only do one thing at once. They don't have any parallelism. They take an input and produce an output, generally. And those first goals when learning a program are to write a correct program, an efficient program, and hopefully also one that is clear or readable, although that's less emphasized. And correctness and efficiency are important, and this class is also going to be about efficiency, but a different kind of efficiency. After those introductory programming classes, up to, let's say, the data structures class that is kind of universal in computer science curricula, after that, the upper level classes tend to be introductions into different areas of computing research. So you start to specialize and go off into different areas. Those are difficult classes and very interesting topics, but typically the programming that students get experience with there is writing very small programs. And those classes are really about, I would argue that they're designed really to prepare students for a PhD program rather than to prepare students for software engineering. Although the topics that are learned very often are relevant for software engineering, what's missing is a preparation for building large software systems. And this class is meant to give to teach that. Okay, because the current state of computer science education is deficient in the sense that I think most computer science graduates are not ready to be productive in their first job. And it's difficult for computer science graduates to get their first job, especially if they go to a smaller company that is not willing to spend a lot of time training them, because they don't have knowledge in software architecture, the kind of thing that we're going to cover in this class. So I'm hoping to fix that problem, both for the good of the field and also for your benefit, so that you can more easily find a job. And also, if you want to start your own company, found a startup, you'll have the information you need to know how to build something from scratch yourself, rather than relying on your elders to tell you how to do it and to give you a little piece of work. You'll have that kind of high level architecture ability. And hopefully you'll get an idea of how common systems that you use every day work. Big online systems like Google Search or Netflix. Right? You'll learn how to build real complex big software services. Of course, you have to know how to program already. So this course is not really about programming, but taking little components of code that are coded up and fitting them together into a bigger system that interacts. Where we have multiple coordinating applications. Coordination is a big topic of this class. You have to be able to scale your load, in other words, to be able to handle more and more load, more and more users without failing. And you have to have some way to deal with an arbitrary number of users, ideally. In order to do this, we need techniques for dealing with big data, both in terms of storage and databases and other storage systems, and also computing systems for processing big data sets. And we'll also learn about how to operate your code in the cloud, on a public cloud. And on the cloud, there are a variety of different computational platforms available, which we'll talk about. Okay, in other words, you'll think about not just your programming language and the code you write in that language, but also where is it deployed, and how that interacts with other programs that might be written in different languages, but all kind of fits together into a big system. Okay, so I would summarize the goal of this class for you is to learn enough to be able to either build your own scalable startup product, in other words, deliver some software that you build from scratch that is able to handle lots of users, or alternatively, if you go to a big company or a medium-sized company, to bypass that on-the-job training that you need, or that self-study that you have to do in order before you're productive. Although I guess there are still going to be other kinds of on-the-job training that you'll do, of course, throughout your career. It's not like this is going to teach you everything you need, but this like gives you that background knowledge that is really, when you step back and look at it, it's pretty basic. But it's not currently taught in other classes. Okay, so we're going to cover. So I categorize the topics of this class into two big categories. The first one is control. Sometimes I also call this coordination. So ways to get different pieces of code in different places to work together. This involves the overall concept of separation of concerns using microservices, having APIs that define how services interact. We'll have a couple lectures on that. Asynchronicity is the idea that you have things that happen at different times, and that coordinating that with either message queues or push notifications. We'll talk about that for a while. Different kinds of parallel processing. So either load balancing, where you have a lot of workers in parallel working on kind of the same kind of work, or more complex systems like MapReduce and Spark that use a lot of computers to solve one big problem, as opposed to having a lot of computers solve a lot of instances of small problems. That's what load balancing does. We'll talk about different platforms, cloud computing in general, then more specifically virtual machines versus containers versus serverless functions as different like units of code and computation that you can deploy. The second big topic is data storage. We'll see later on that databases, whether we're talking relational or NoSQL databases, are like a fundamental topic you need to master if you're going to build a big system. Every big system has some kind of database or distributed file system. That could be another thing we list here. That allows that bunch of little components, lots of thousands of computers, let's say, to act as one big system. They need some kind of like sharing of data, right? And in general, we call that a database. Another aspect of data storage is caching and content delivery networks, which are more at the front end. We'll talk about those later, though. And I'll try to use as many case studies in this learning as possible. So, for example, we'll look at the architecture of Wikipedia. We'll look at a few parts of Twitter. I'll talk a little bit about Netflix and some other examples as well. I think also maybe YouTube. And then you based on those examples, you'll go on to look at other. You'll be able to go on and look at other examples, and build those yourself. At least design them on paper, right? So for some of these case studies will be used to illustrate a particular concept. We're not going to, like for example with Twitter, we're not going to look at the full Twitter architecture. We'll look at one particular aspect of it to illustrate a particular point. With Wikipedia, we're going to look at quite a lot of it actually to begin with. We'll see. Okay, so I've told you a little bit about what you'll learn. What you will not learn is machine learning, just because everyone wants to learn machine learning these days. Unfortunately, this class is not going to teach you too much about that. We're going to talk about databases, but we're not going to talk much about internally how databases are implemented. There are like separate classes for that, dedicated to that. We're going to talk about cloud computing, how you use cloud computing as a customer, but we're not going to talk about how cloud computing infrastructure is implemented internally. So like virtualization, software-defined networking, that's beyond the scope of this course. We're also going to we're not going to talk about the details and the theory of distributed systems. There's a class dedicated to distributed systems. That's a full term where you learn about things like consistency and clocks and stuff. So we're going to be dealing with that only at a higher level, not in the details. So you can also take that class to supplement this one. Okay. So like I said, in this class you're going to learn to build real complex big software services. So building something like Google Search or Netflix. Okay, yeah. Actually, this is a duplicate slide, so let's move past it. Oh, I went back. Okay, so to summarize that, the topics we'll cover include service-oriented architecture, so breaking your system into multiple pieces that coordinate through APIs, different kinds of databases, caching, distributed message queues, parallel processing. I kind of already said that. Case studies, I mentioned that. Okay, so in today's introduction, I'm going to talk a little bit. I'm going to introduce some pretty basic concepts, so it's a kind of a slow, easy start, I think. We're going to talk about the difference between a standalone application and a service, and I'm going to talk about some simple definitions of scalability. Okay, and start to give a hint as to why scaling is difficult, or what particular things about scaling are more difficult than others. A traditional view of software scalability from a computer science academic perspective that you would learn starting in a data structures and algorithms class, and then later on in more advanced algorithms classes. In that view of scalability, we're looking at input data size for a problem, which we typically notate with the variable n. As this n gets bigger, as input data gets bigger, we want the program to run quickly. And we measure the relationship between the program runtime and input data size with complexity analysis, which you've probably seen with big O notation. So, for example, if we're talking about sorting, merge sort is an efficient, popular sort. Given a list of n items that need to be sorted, it takes n log n time for merge sort, in the worst case, to run. Okay. Similarly, if you have a hash table of size n with n values, you finding a particular value on average takes constant time, big O of 1. That's a kind of scalability analysis that's useful, but it's not exactly what we're going to be covering in this class. So in this traditional view of complexity analysis, we're assuming that we have one problem to solve and we have one computer. All operations have the same cost, and we want to optimize our algorithms to do the best possible job with that one problem on that one computer, which is all well and good, and you need to know that stuff. But in this class, we're going to be talking about different types of scaling that involve multiple computers, and that involve primarily dealing with how many parallel requests you can handle at once, as opposed to what is the efficiency of each individual request or program. We're still going to use traditional best practices from data structures and algorithms to implement our services, but that's not the focus of this class. We're going to assume you already know that stuff. In this class, we're going to think about how to scale it out to do a lot of stuff in parallel. So a service is different than a program insofar as it listens for requests from clients or users, and those clients could be other computers, or they could be human users. And the service can handle multiple requests concurrently, meaning at the same time in parallel. You have some outside user or program that provides an input, which is called a request, and the service's job is to output a response. Okay, so instead of using the terms input and output, we use the term request and response. The requests are usually delivered as messages that arrive over a network, and the responses also are delivered as response messages over the same network. The service is expected to run constantly, waiting for these requests, and it processes them as they come. Okay, so services typically is not code that you run on your laptop, because your laptop's not on all the time. It's battery powered. You shut it, you close it when you're not using it. You move around. Typically, services are run on servers. Servers are the machines that are in data centers. They're always powered on. They don't have keyboards and mice hooked up to them or monitors. They just live quietly not actually loudly in data centers or server rooms, whether it's your own machine that you've put in your own server room, or it's a machine that you've rented from a cloud computing provider in one of their data centers. So as an example of a service, you can consider just like a website. So this URL is a web URL that would bring up a page for search results for guitars that are on sale on eBay. And you can have many users at the same time that are making a request to view all the guitars that eBay has for sale, right? So service scalability is about how many users the service can handle at once, basically. How many concurrent users or requests can be handled. When we say a service is scalable, that means that it can easily handle growth in the number of concurrent users or requests. So scalability metrics are measures of work throughput. So throughput is like how many things per second, right? whether it's requests or queries per second, or maybe bytes per second, or you could measure it in terms of the concurrent number of concurrent users at more of like a human level, or even the number of monthly active users, if you want to zoom out from now and consider like a long time scale. Those are all different ways of measuring the scalability of a system or a service. So for now, we're not talking too much, or we don't care too much about the cost to achieve this scale. But we just primarily we want to be able to scale to the largest degree possible. So to be able to handle as many users as possible, basically. Although, we will choose strategies that ideally minimize the cost of doing so. Usually the cost of handling. If you can minimize the cost of handling, let's say 1 million users, those same strategies generally allow you to grow to, let's say, 10 million or 100 million users. But there are some breakpoints where different decisions are needed. Okay, so that's a basic definition of service scalability. I want you to stop and think now about why it might be difficult to make services big, even if money ain't a thing. So even if you have unlimited money to spend, cost is not an issue, but you want to make, let's say, your website handle, 100 million users every month, or 1 million users simultaneously at any given moment. Why might that be difficult, even if you have unlimited money to spend? So remember, this icon in the lecture indicates that I'm asking you to pause the video and think about this question for a moment to help you to interact, have a more interactive experience and learn more during the process. So please pause and think about this question. Okay, so I'm assuming that you paused, you thought about it, and now you're continuing. Well, I'll give you some answers to this question. So when you talk about everything we know about computer programs so far from introductory programming involves programs running on one machine. Any machine has limited speed, and you actually can't buy a machine that's arbitrarily fast. So that in itself is a limiting factor in scaling. So we need to have multiple machines somehow to handle the service. Once we have multiple machines, those machines need to be coordinated somehow. Like, we need to figure out which machine does what work. For example, if we have 1 million users accessing the eBay webpage, each user needs to be assigned to a machine that handles its request and gives its response. We need to share data among those multiple machines, like those various servers that are handling the eBay website need to all access the same list of auctions, and auctions are changing. When a bid is entered, for example, that bid needs to be visible to all the different machines that are handling requests to return auction results. Okay, so we need to be able to find the data, we need to manage competing requests to change the same data, and we need to propagate changes to the data to all the different machines that are accessing that data. So that itself is a challenging problem. When we add more machines, there also is a greater probability that any one of them will fail. So if you have a system that relies on every machine working and not being crashed, and if you have one machine, then fine, that is you actually have a good chance that you can run for, let's say, several years without having a hardware failure on one machine. But if you suddenly have 1,000 machines instead of one, now your chance of having a machine failure on a given day are like roughly 50-50. Okay, so your system at that point, when you've scaled to lots of machines, you can't design your system such that it relies on the absolute reliability of all your components. You have to have some redundancy. You have to have some mechanisms for dealing with failures. And of course, you want to have that anyway, even if you have just one machine. But the important thing is it becomes way more important when you have lots of machines, because, like I said, once you move to 1,000 machines, now suddenly every other day you're expecting a machine failure. When you scale, you're going to have users now that are distributed worldwide. So communication latency becomes a problem. By latency, I just mean delay. So the speed of light, it limits communication on Earth in the universe. So if I want to send data from, let's say, Chicago to Beijing in China, the time it takes for that data to travel is something, if I remember correctly, it's like 150 milliseconds. So to get data and get a response back, I can only do that like 3 times in a second. That's really pretty slow when we think about how fast computers do other things. So you want to minimize the amount of like long distance communications you do, yet at the same time you want to have computers all over the world. They're like working together on the same data set and serving users that are accessing the same service. Okay, so that latency becomes a challenge at high scale. We also, when we have multiple computers that are coordinating, we have the need for them to be able to trust each other so they can work together, like to share data. For example, if one machine gets a new bid from an eBay user, that bid needs to be entered and like recognized by all the other machines. But at the same time, we want to ignore interference from attackers. We have to rely on requests from the network to do our work because there are multiple machines. Yet at the same time, we don't want to accept bogus requests from attackers. So we need some kind of authentication so that we know which requests to trust, which machines are our friends, and which ones are our foes. Okay. Finally, when we have a big system, we have to do software updates, and those updates should be done without downtime. I guess that also is true of a system that only has one computer. But anyway, if we're thinking about a service as being on all the time and handling requests from lots of users, there's never going to be any time when there's not a need for someone to use your system. So in fact, software updates become more challenging. We don't want to have downtime. All right, so I hope that you thought of at least some of these. I'm sure that you didn't think of all of them, or at least I don't expect you to. But this class will help you to reason about all of these things. Okay, so the first kind of scaling we're going to talk about, mainly just in this lecture, is vertical scaling. And this, because it's the simplest kind of scaling, what we're going to do is assume that you're starting off with a very light load and you can handle all the requests on one machine. Like let's say it's your laptop, right? You write some code that runs on your laptop. Okay, scratch that. Let's say we are doing a service. So laptop's bad because it's not on all the time. Let's say you bought a machine, you installed it in a data center or in a server room. You hooked it up to the network. You loaded your code on there, and you're running a website. Like let's say you're running a competitor to eBay, some auction website. Great. Okay, but it's on one machine. Suddenly your demand increases, like you go viral, right? So you have a lot more users. Great. At some point, that machine is too slow to handle all those requests. Now, the easiest approach to scaling your system is to just somehow buy a faster machine to run your service. And that is what vertical scaling is. So we're going to talk about both vertical and horizontal scaling in this class, and this picture will help you to remember what that means. So you have computers that all kind of stand next to each other, and if you are making your machine or machines bigger, think taller, and that's vertical scaling. So making your machine faster, stronger, taller is vertical scaling. That's easy in the sense that it doesn't require you to change your code or to change your overall strategy, right? You just throw money at the problem. Of course, no one wants to spend more money, but in some sense it's inevitable. If you started off with just the right size machine for your original load, like you started off with a cheap machine and then you get more demand, then it makes sense that you're going to have to buy a more expensive machine to handle that greater demand. Horizontal scaling is different in the sense that it doesn't involve buying faster machines. It involves just buying more machines and standing them side by side so they can share the work. Okay, that's horizontal scaling. And most of this class is about horizontal scaling rather than vertical scaling. We'll see why soon. Okay, so let's have a quick intro to computer engineering. Okay, so I was a computer engineering major, so this is one of my favorite topics, but we'll just briefly talk about this. So what are the things that affect computer performance and why is it limited? So if you're shopping for a computer and you want one that's fast, the things you would consider are the number of CPU cores, that determines the number of things you can do in parallel on that machine, the speed of each CPU core, which determines how fast each process or program runs, And finally, related to that is how much competing work is happening on that machine. So if you're sharing the machine with a lot of different programs or we call those processes that are running, then that's going to slow down your task, right? At the same time, there's some other secondary things that might affect your performance. So the amount of memory on your computer, which is called RAM, physical memory, that might make that might affect computer performance. Like if you don't have enough memory to fit all the data that's needed for your program execution, then that'll make your program slow. If you already have plenty of memory, adding more won't make it faster. So that's why I say this is a secondary thing. The type of disk that you have on your machine affects computer performance. This actually could be pretty significant if your program does a lot of disk access, like it loads a lot of data from files. Some disks are faster than others, like solid state disks are faster than those spinning magnetic disks, but the capacity is less. There also are different kinds of solid state drives, like the NVMe ones, like the PCI Express connected drives are faster than the serial ATA drives. Also, but again, that only is relevant if your program is doing a lot of disk access. At the same time, if the number of disks you have could make your program run faster. If you're doing a lot of disk access, and by having multiple disks, you can do access in parallel, especially, and that's easy to implement actually, even without changing your program logic, using a system called RAID, which takes your file system and splits it automatically over multiple disks, and you access them in parallel. Your network connectivity type, like the connection you have to the outside world, and the network adapter that you have, the type of connection that's physically on the machine, could affect your computer performance if that is a limiting factor, like if it's sending a lot of data in and out. And finally, you might have some kind of special purpose accelerators on your computer that would make certain computations faster, like GPUs, which are graphics processing units, tensor processing units. Those two things are useful, especially for machine learning workloads, and also graphics processors, obviously for graphics stuff. And there are other special purpose accelerators you might have that make certain computations a lot faster. But there's a limit to how fast you can make a computer, certainly with these primary factors, because CPUs have limited speed, which I'm not going to get into why, although it's a fascinating topic, which we could talk about in office hours if you're interested. Okay. On a given machine, so in this world where you only have one machine, you can buy a more expensive machine to get more CPU cores and faster CPU cores and more memory. If you get a machine that has lots of CPU cores, that allows you to do more things in parallel on that one machine. What you may not realize if you haven't taken an OS class is that even on one machine, there's a lot of things happening at the same time, a lot of concurrency. On your laptop, you probably have about 100 processes or programs running at any given time. Although your laptop probably only has about 4 CPU cores available to run things. So only 4 things can really run at the same time, truly. What happens is the operating system schedules processes so they take turns using those 4 CPU cores if you have 4. So most of the time processes are not running. Sometimes they might be not running because they can't. They're going to be blocked, which is waiting while they're doing some kind of input or output. Like if your program reads from the disk or over the network, makes a network request, it might be waiting for a message to arrive over the network. Those are all things that would stop the program from running. If the program blocks in that way, the OS knows that it can schedule something else to run instead. While a process is blocked or descheduled, another process can take over using the CPU. So your operating system kind of alternates the programs on the CPU. So they all take turns using the CPU. In addition to that, to having multiple processes running at the same time, a single process, like a single program, can have multiple threads of execution, which can execute concurrently while sharing the same memory. This is called shared memory parallelism. So this is where you can have multiple things happening at once in your program, like multiple functions being called, for example, different paths being executed through your program, but using the same data. And that's a way to make use of, let's say, your 4 different CPU cores at the same time with a single program. Okay. So an example of that, I'm showing you here an example of like parallelism on a modern machine, modern operating system that takes advantage of multiple CPUs. So on the left-hand side, I'm showing the output of a program called top, which is a Linux utility, or generally a Unix utility, that shows the processes that are running on a computer. So every row in this table is a different process running on my computer. This example is a little virtual server that I use to run my website and some other things. And this virtual server is small. It's technically called a T2.micro sized virtual machine from Amazon Web Services. It has actually 1 CPU core, and it only has 1 gigabyte of memory. So it's really quite tiny, and it's cheap. Like it costs something like $8 or $10 a month to rent this machine, this virtual machine. On this virtual machine, there's a web server running. The particular web server is called Apache, and the process, you'll see it shows up as httpd.worker. So this web server program is running actually 11 separate times on this machine, even though there's only 1 CPU core. The reason for that is because it wants to be able to handle requests in parallel. Any one request to the web server might take a long time to work as it does things like read files from the disk. Like if someone makes a request to the web page, it might have to load an image from disk or an HTML file. While that is happening, while the disk is pulling up the data, in other words, the program can't really make any progress. So the operating system can take that program and set it aside, like unschedule it, take it off the CPU, and let another program run. In this case, we have the 11 different copies of this web server program can like take turns running, and they can all kind of in parallel handle different requests, even though there's only 1 CPU. This is an example of, I guess, how parallelism works in practice on a single machine through the process scheduling. Okay. Now, cloud computing makes scaling easier for a couple of reasons. So it makes both horizontal and vertical scaling easier. So let's talk about vertical scaling first. So cloud computing is the ability for you to rent a virtual machine, essentially, from a company like Amazon or Microsoft or Google or Alibaba. Okay. When you rent one of those machines, you can specify the type of machine that you're renting. And specifically, you can specify the number of CPU cores, the amount of memory, the type of disk, and so on. So with Amazon, they have different classes of servers that have weird names like T3.nano and M5D.24XL. So these are 2 different extremes. So T3.nano is an example of a really small virtual machine. It has technically 2 cores, but you're not allowed to use them all the time. So it's actually less than 2 cores. If you use them all the time, then it'll like stop giving you 2 cores. There's half a gigabyte of RAM, which is tiny. That's equivalent to a computer from like my college days. So like, think of like 2004 or 2003-ish, maybe something like 2003 is like when you'd have a machine with that much RAM. It has a solid state disk that's not in the machine, but somewhere else. And this machine costs half a penny every hour to rent. So over the course of a month, it costs, I don't know, something like $5 to $10. On the other extreme, you can get a machine that costs, let's see, this is 1,000 times more. This is a machine with 96 cores instead of 2. It has almost 800 times as much RAM, so 386 gigabytes of RAM. It's got a fast solid state disk in the machine itself, so it has very fast disk access. And you're going to pay a lot more for it. So $5 an hour is going to really add up. So that'll cost you like $5 an hour times 24 is $125 a day times 30 is 1,000. It's going to be like $4,500 a month for a computer rental. That's a lot of money, right? Okay, so we had that range of options, and you have the option not just to choose your size to begin with, but to change your size. So if you set up a machine, if you rent one of these machines, you get an operating system, you can log in and like start installing your software, set up your database, your website, whatever it is that you're running on there. And then you decide, oh wait, this is too slow or this is too fast. What you can do is reboot. You can, in the web interface or through an API, you can change the size of the machine and reboot the virtual machine. And then when it restarts, just as quick, in let's say a minute or so that it takes the OS to reboot, when it starts up again, it'll be migrated to a different sized instance, and you'll have more or less resources available. So that's convenient for scaling, right? There's a little bit of downtime there, but it's fast. Certainly a lot easier than in the old days. You'd have to like buy a different sized machine and install it, right? Cloud computing also makes horizontal scaling easier because you have the ability to purchase more virtual machine instances at any time. You also have the ability to do the reverse, which is to shut down virtual machine instances, and you're billed every like hour or 15 minutes or minute, depends on the service. So you can shut down a machine after using it for only an hour and only pay for an hour's worth of usage. So you can just scale things up when you need the load, when you need the capacity, and shut stuff down when you don't need it. In that sense, cloud computing is elastic. When we use the term elastic in cloud computing, that refers to the ability to like quickly change the size, to stretch things and shrink things. And that's why the very first cloud computing service that was quite popular for Amazon was EC2, which stands for Elastic Compute Cloud. And before it was called AWS, Amazon Web Services, the service was just called EC2. And that was the extent of their cloud computing service. Now, of course, nowadays there's a lot more that they offer than just EC2. Okay, so vertical scaling, remember, is changing the size of your machine. The pros and cons here that I have here in two different columns. The pros are that when you're, it's easy to write a program that runs on one machine. That's what you're used to doing, and there's no special coordination required. So if you can handle everything in one machine and vertically scale it, and that's good enough for the lifetime of your application, that's great. It's easy. Most languages have support for multi-threading, so that if you scale up to a big machine that has, like, let's say 96 cores, your language will be able to handle the parallelism to support all the cores in that machine. There's a lot of off-the-shelf software that's written to run on one machine. So, for example, relational databases like MySQL or Oracle, web servers like Apache, Nginx, or Node. That's software that will run on a single machine, and then you can scale that machine up to handle more load. Modern servers have a lot of cores, like 96, so they can do a lot of work in parallel. In the old days, like before, roughly 2007-ish, when computers got faster, it was like just one core, but the speed was getting faster. At some point, that was no longer possible, so they started. What they could do was just put more cores in a CPU, and that's now we have a ton of cores available in a computer. A computer can connect to hundreds of disks, and to get huge file storage and file access throughput on a single machine, so that allows vertical scaling to happen. And by building a system that only has one machine, we avoid the cost of communication between outside machines. So, in some sense, it's actually more efficient to use a vertical scaling approach for like small and medium-sized problems. And that's why, for example, a lot of commercial, like enterprise databases like Oracle is a database that's used by big companies. But essentially, when you look at it, it's really just designed to run one machine. Although there are ways that it has backups and redundancy with a few other machines. But essentially, it's a software that runs on one machine. The downsides, though, for vertical scaling and like the single machine approach are, at some point you're going to hit a limit. If you're YouTube, there's no way you're going to handle all the traffic they get with one machine. If you want to handle really huge loads, you need to have multiple machines. Okay, so you have to pay that cost of like complexity of your program and communication between machines. You need to somehow solve that problem. This class is going to be about how we do that. Another downside with vertical scaling is you can't quickly scale vertically. Like you have to reboot your machine if you're going to change its size. Horizontal scaling can be a little faster because you can add machines more quickly. You often have a single point of failure with these single machine designs, and the price performance ratio actually is pretty poor for top of the line machines. So as you try to get the absolute best performance out of a computer, at some point you get to a scenario where you're paying a lot of money for just a small percentage. You might have to pay twice as much for a computer that's only like 20% faster. That's how the pricing of CPUs works, due to like the difficulty of producing a CPU that's really fast, doesn't have any defects that make it slower, and also due to like the way that CPU manufacturers have chosen to price their CPUs to meet demand and to make the most profit. In addition, the motherboards that support lots of sockets to have lots of like CPU lots of CPUs in one machine, to have like the 96 cores in one machine is actually multiple CPUs on a dual or quad CPU motherboard. Those motherboards are expensive. So the price performance ratio is kind of poor for top of the line machines. So in some sense, if you can split it up, you might save money at some point before you reach the limit of vertical scaling. Okay. So to summarize, vertical scaling is not truly scalable. It's only scalable to like a small or medium scale. Beyond that, everything needs to be done with horizontal scaling. And this class is going to focus on horizontal scaling techniques. But, I did want to first talk about vertical scaling because that'll be useful for certain applications. Like the website that I run, the National Gun Violence Memorial, it uses vertical scaling. When the traffic goes up or down, I just change the size of the instance, and that's good enough to handle that website, which is like has medium-sized traffic. At any given moment, they're like on average 150 concurrent users, so it's not trivial, but it's well within the limits of a single machine because machines these days are pretty fast. We're not talking about Google and Facebook size scale. Whereas this class will teach you techniques that do handle that huge scale. Okay, so horizontal scaling is needed for global apps, for huge apps. Public cloud computing providers give you access to lots of machines, but you need to learn the techniques to make good use of those machines. It's actually quite difficult. And like I said, most of this class will address the coordination of execution and data that you need in those horizontally scaled systems to solve those really tough horizontal scaling problems. Okay. So in this lecture, I talked about software services, defined those as a program that runs continuously, giving responses to requests. The kind of scalability we're going to be talking about in this class is the ability to grow a service to handle many concurrent users, and ideally an arbitrarily large number of users. And then I talked about two different approaches to scaling that are useful in different scenarios. Vertical scaling is like the very simple one where you just upgrade your machine to make it faster. This isn't true scaling because there's a limit, right? There's a ceiling to how fast a single machine can get. Horizontal scaling, on the other hand, is when you add more machines to do more in parallel, in that you can keep adding machines infinitely, and so that's ultimately the approach that we want to learn because it gives us the most power, but it introduces a ton of challenges. Okay, and the rest of this class is going to be about addressing those challenges, describing different ways we're going to organize those machines, and so on. Okay, I hope that gave you a little bit of a taste of where we're headed. That's just a start. We're going to have about like 17 more lectures on this topic, so stay tuned.